Logs. Do you remember loving logs?
Yeah. Automatic.
Okay. Connor, just take your headphones off for me. All right, so the big thing with logs, just for today getting started, is understanding the way logs are just a different way of doing something that you already know, and it's exponents. Logs and exponents are pretty much the same thing, but I like to think of it as a translation between languages. So this is log language. That's like French or Spanish right now. And anytime you hear something in French or Spanish, you convert it in your head to English so that it makes sense to you, right? Unless you're fluent and then you can think in that language, but we're not. So this is a different language. You need to know how to rethink of this so that it's appropriate to the language that we know, which is exponents. Yes? So log language, exponent language. So the equivalent translation for this, how do you guys read this? Ryan, if you were to read that, what would you say? Base B of x, yes. So you do have to say log, you can't just say log bx. That doesn't make sense. It's log base B of x. So whatever the base of your log is, that's also the base of your exponent. So B, and then it's always raised to whatever's on the other side of the equal sign. So in this case, it would be the base of B raised to the other side, which is y, equals whatever you're taking the log of.
So what is that? Oh.
So log language, exponential language, but those two things mean the exact same thing. Okie doke? So if you're changing from log to exponential, to me, this is the easiest way to go, just because I think I constantly repeat this phrase in my own head. The base is 5. Raised to the other side is 2 equals x. This one I think is harder because you're trying to go back. So it's log with some base of some number equals something. So it's the base. So what's the base over here? E. Raised to the other side. So what's it being raised to? No, E is being raised to y. So if you go to your log, it would be E raised to the y. Equals 9. So because I do think it's easier to go from logs backwards, because that's the foreign language back into your native language, I would kind of play around with this side and then just make sure your base of E raised to the other side y equals 9. Does that make sense? So when you're evaluating, you're trying to figure out what this equals. So set it equal to x and then translate it. So Faith, how would you translate this log language into exponential language? What's your base? Raised to the other side. What's the other side? Right. And then thinking about that and what x equals is easier. Depending on who you have, I know Mrs. Ziggy says this a lot, but I don't know about the Hills. Do they ever refer to this as like the what power function? Right? So essentially you're being asked 2 to what power equals 16, and that's what the translation turns it into. So 2 to what power equals 16, so x would have to be 4. And so your evaluation log base 2 of 16 is 4. So if you think about it that way instead of translating, then in part B you would pretty much ask yourself 25 to what power is 5? I heard 1/5 and 1/2.
1/2.
So if we translate it, 25 to x equals 5. If you know your exponential fraction properties well enough, you would know what that is. If you don't, you can always change 25 to 5 squared. So 5 squared to the x power equals 5. And then when you raise a power to power, what are you supposed to do? Multiply. So 5 to the 2x equals 5 to the first, technically. And then your bases can cancel. 2x has to equal 1, so x is 1/2. Which is right, 25 to the 1/2 power, because raising to the half power is the same as the square root. Okay? There's common logs and natural logs, both of which you did last year. Common logs have a base of 10. Natural logs have ln, or ln. That's just log base e. So common log, so like on your calculator, if you would just hit the log button, like if I just hit like the log of 100, the base doesn't come up, but the calculator is assuming that's 10. So what should this give me? The base of 10 to what power is 100? So that should give me 2, and it does, right? Do you remember how to find the log with the base on your calculator?
Yeah.
I think it's math, number, no. It's just math, and then it's right on that screen. You just have to scroll down. Don't go over to number. Yeah, log base. And if you type in that log base, it'll come up with the little empty boxes that you have to fill in for the base of the log and for whatever you're taking the log
My
of.
log base is disabled.
Yeah.
Oh, I shouldn't do
I'll have to Google that later for you. Yeah.
I'm going to figure it out right now.
Okay, good luck. All right. So, common logs base of 10, natural logs base of e. So here's your basic properties. And normally, I wish these were kind of left blank so we could fill them in together. But log base b of b. Really, you're asking yourself, the base of b to what power gives you b? And so that's why that is 1, because b to the first power is b. So anytime you see something like log base 7 of 7, that's just 1. Log base 12 of 12, that's just 1. Okie doke. If you're taking log base b of 1, you're being asked the base of b to what power gives you 1. And anything to the 0 power gives you 1, which is why that's 0. So if it's log base 7 of 1, anytime you're taking the log of 1, the answer is 0. Because your base of 7 raised to the 0 power on the other side equals 1. If you're just asked for the log of 10, that equals 1, because that is the common log, right? If you don't see a base, the base is 10. So in number 3, that's really log base 10 of 10. And you can see now it actually is the same property as property 1. They just didn't write the base because it's the common log. Log of 100 is 2. Log of 1,000 would be 3 because it's always 10 to what power? Okie doke?
Wait, so log 0, 10, is that what it is? The third one?
It just says log of 10. There's no base.
But what did you say?
Log base 10 of 10. Because if you don't see a base, you assume it's 10. On the right side, so again, I wish these were blank, but if you ever see log base b of b to some power, this is really this property 1 over here put to use. The log base b of b part cancels, and your answer is just whatever the exponent is. So for example, if I do log base 7 of 7 to the 4th, the log base 7 of 7 cancels, and your answer is just 4. And you can see why over here in example 1. Your base of b raised to the other side, x, equals b to the x. Just pretty much says b to the x equals b to the x. 2, b to a log base b, that also cancels. So if you ever have 7 to the log base 7 of 5, that's just going to be 5. number 3, finally, we see ln for the first time. Because that is technically log base e of e to the x, again, log base e of e cancels, and that's just x. So a natural log and an e cancel. You probably did that a lot last year when you were solving equations. That's how you got rid of an e, is you just took the natural log of both sides. And then in 4, same thing, e to an ln, those cancel, and so it just equals x. So on the bottom, log base 7 of 7 is what? 1. Log base 8 of 1 is what? 0. No. 8 to what power gives you 1? 0. That's property 2. Log of 1 is always 0, no matter what the base is. Log base 4 of 4 to the 5th will be what? 5. And 6 to the log base 6 of 9. Good. And then lastly, the domain. Do you remember what a log function looks like? That's never going away. 1 second. Like if I did the parent graph for log of x, do you remember from last year what that looks like? Like it, well, window will do -5 to 5 will be easier. So it comes down here and it shoots down. You remember that? So just draw a quick sketch of that. There's an x-intercept at 1. And there's an asymptote on the y-axis. So if you're looking at the domain of that function, what is it? 0 to infinity. And does that include 0 or not?
No.
No, because that's an asymptote. So your x coordinates are anything past 0 to infinity. Good? Your range is -infinity to infinity because it goes down forever and it does increase forever. This is log y equals log of x. What does it say? So the reason I bring this up is because it visually shows you that you're only allowed to take logs of positive numbers, right? If my domain doesn't include negatives, that's because if I try to take the log of a negative number, I'm going to get an error. If I even try to take the log of 0, I'm going to get an error. I can only take the log of positive numbers. It can be a tiny positive number, but I can only take the logs of positive numbers. So when you look at a function, you essentially look at whatever you're taking the log of, and it has to be positive. So in this case, x plus 3 has to be greater than 0. Solve that, and that's your domain. So if I subtract 3 from both sides, x is greater than -3. That's my domain. In interval notation, that would be -3 to infinity. Good? This next one's a little bit trickier because it's a fraction. So 1 plus x over 1 minus x has to be greater than 0. So solving this algebraically is a little bit tricky because you'd probably want to get this out of your denominator, right? So you'd have to multiply both sides by 1 minus x. The issue is, since this is an inequality, if I'm multiplying both sides by 1 minus x, because I don't know what x is, I don't know if I'm multiplying by a negative number or a positive number. So I don't know whether or not I need to switch the direction of the inequality. Does that make sense? So, what did you say? Well, we solved fractional inequalities way back in the beginning of the year, I think. Solving equations. Hold on. I'm going to refresh your memory. Solving inequalities. Anybody remember? Inequalities review. We solved linear, we solved absolute value, we solved polynomial, and we solved rationals. This. Remember how we did that? No. So we have to do a number line test. You find so if you think about rationals and we just graph them, we're essentially looking for where this graph is positive, greater than 0. So when you have like vertical asymptotes and horizontal asymptotes, your graph can go from being in the positives to being in the negatives surrounding a 0, or it can go from being in the negatives to being in the positives surrounding an asymptote. So you get critical points on a number line where the graph probably is transitioning from being negative to being positive. So we'll set up a number line based on our x-intercepts, or our zeros, which come from the numerator. So that would be an x value of -1. And it's greater than 0, so that's going to be an open circle. And then your asymptote, which regardless will always be an open circle, is where? Your vertical asymptote. +1. So these are the values I have to test in between and outside of to see where this graph is actually greater than 0. So if I plug in a 0 in this middle section, I'm going to get a positive over a positive, which is a positive. So that is greater than 0, so I shade that in. If I plug in a 2, I'm going to get 3 over a negative, which is a negative, so that's out. And if I plug in a -2, I'm going to get a negative over a positive, which is a negative, so that's out. So my domain for this is just x's between -1 and 1.
The log is good.
Not at all. It's just whatever you're taking the log of. Your bases have to be a positive number, though, too. You can't have negative bases. Just like in exponential functions, you can't have negative bases. So that's going to require you to kind of remember that. So separately, I'll show you the graph of just that one, 1 plus x over 1 minus x. And we were looking for where this graph is positive, and you'll see that it's positive from -1 to +1, and then it's negative the rest of the time. Everyone see that? You had a 0 at -1 where it started being positive, and you had an asymptote at +1 where it jumped over and became negative. So it was only positive between -1 and 1, and that backs up what we found. If I graph this one, you'll see that the graph only exists because this only has a domain between -1 and 1. So math, log base 5 of 1 plus, is it 1 plus? Over 1 minus x. So this graph, that's it. It only exists because that's the domain of it between -1 and 1. Which came from this one only being positive between -1 and 1. Okay. Last one. Log base a half, again, means nothing. Whatever you're taking the log of this has to be greater than 0. This is more of a thought. There's not really much work to show. But if this has to be greater than 0, what values of x are appropriate? Say it again.
I believe it's 0.
Everything besides 0. So +1 works, -1 works. Because when you take the absolute value of things, they always become positive, unless you're 0 itself. Because the absolute value of 0 is 0, and that's not greater than 0 like it needs to be. It equaled it. So this would be all real numbers except x cannot equal 0. So x is any real number, but x cannot equal 0. Interval notation, that would be negative infinity up to 0. Union with 0 to infinity, just keeping parentheses around the 0 to exclude that. Any idea if, pretend, if log base half of x looks like that, what would the absolute value sign do to that? Guesses?
Do the other thing the same side of the mouth.
How do you know all this, Connor? I'll give everybody up. Connor. So there's the log base of half of x. And if I throw an absolute value sign in there, log base math, log base 0.5, and I throw in the absolute value of x, he's right. Really, because now, all of a sudden, log base of half of x, whether you plug in a positive 5 or a negative 5, it's the same value, right? And so what would you call this function, even or odd? Even, right? Because it's symmetrical to the y-axis. It's symmetrical to the y-axis because when you plug in a negative x, it's the same as the original. So basically properties and then just knowing how to find the domain algebraically, and that's where we're stopping. So, Ryan, take one pass it on.